part for the input-output. Your CPU will need to interface itself to other integrated circuits and other, in general, the rest of the world. So you need to have the general purpose I/O. You need then to know about essential peripherals that are used in pretty much all kinds of applications in general. You need to know about digital to analog converters. You need to know about analog to digital converters. You need to know about timers. You need to know about serial communications and how they are implemented in the circuitry in your microcontroller. Then we see about your general purpose input-outputs. They are your interface for everything that is outside your microcontroller. They provide as an input and output for electrical signals, and you can access them by the pins on your microcontroller. You have input and output buffers that are governed by software, and then you need absolutely a level shifter to interface with especially the digital portion. That, of course, in fact, when you provide 3 volts, your microcontroller will not work at 3 volts, because if it does, it will be destroyed immediately. So you need a level shifter at least. You have some I/O logic that generally by itself is maybe another peripheral, and it will communicate with other peripherals directly or your CPU. Of course, you can use these signals as interrupt sources for your CPU, or you can also read them directly. Let's go now to important peripherals. You have the digital to analog converter is a device that takes a digital signal that you have inside. It's a number, and it translates it in an analog signal that you can use with analog. You can use it, for instance, to drive a DC motor, to drive a BJT, and so on. It can be useful to generate a specific also waveform, like a sine wave or triangular wave, and so on. This, what you see like above my head, is implementation that you will find in most integrated circuits, because it's cheap to do. Your analog to digital converter is a device, a peripheral, that will take an analog voltage from the external world. It will take it and convert it into a numerical value that you can then elaborate. And for instance, it is very useful for some kinds of sensors. You can have thermocouples, you can have all effect sensors that give you an analog value, so you can read it and then directly have your measure. You see that there are several different types of analog to digital converters for different kinds of situations. Your faster one is the direct conversion flash, or you can say flash ADC. You have a subsequent approximation register, which is the one that will be used in your microcontroller probably. Then you have integrating ADC, you have sigma delta ADC, and so on. Here we see some circuitry examples for sigma delta, which is one of the most easy to do, just one integrator, one threshold, one bit digital to analog converter. It can be more bits, but one is more than enough. Your subsequent approximation to register, which is the one that is used in our STM32L0 microcontroller, so you need to know it. The flash one, it is a very big circuit, so it is not usually in your microcontroller. Integrated ADC is good, precise, but it's very slow, so maybe you will not use it. As again for the STM32L0, you see that the implementation has a resolution of 12 bits. It can oversample with up to 16 bits, meaning that it can take automatically more than one measure and give you automatically the average. In order to improve the precision, it can also give Gaussian noise, add Gaussian noise to your signal. So in that case, you will have a more precise output, because you see, if your signal lies between two logic levels, it may be when you do the average, you will not have the good. It will not be good. But if you have a noise good enough to switch between one level and another, when you do the average, it will be a better value actually. When you work with your ADC, you should, first of all, especially in your STM32 implementation, if you are multi-channel, use it. It can be interesting, especially if you don't need to do very fast conversions. Then, if your CPU is busy doing computation, you can also govern your ADC with a timer, start with a timer, and use the DMA to transfer the measure directly to some memory part. And then, as I was saying, the noise can be your friend if it's white noise, but you have circuitry for that, but it can also be your enemy. Then you will have your comparator. Your comparator is a circuit that is similar in some regards to your ADC, because it will see your analog value and read something from it. It's like a very simplified version of it. You just have your analog value and a voltage threshold. What you will do is just tell you if its value is lower or higher than your threshold. Try to use this instead of your ADC if you have opportunity, because it has a much lower value, like much lower consumption, and of course it is much more granular, just it is lower or higher. Of course, this is the trade-off. In your STM32L0 implementation, you can set up your voltage threshold by software, or you can also do some trickery to give a threshold that you decide yourself from an external GPIO. Speak about timers and counters. These are another kind of peripheral that is very, very, very useful, and it is used to keep track of timing and events. The circuit, proper circuit per se, it is basically unchanged since the first implementations, and if you read about maybe the Z80, you can also gather some information from the most recent ones also. Regarding the implementation, your STM32L0, we see that you have a 16-bit resolution and upper scalar that can be more or less wide, and you have a low power version. You can even as an output connect to a GPIO and do, for instance, Pwm modulation. If you don't know about Pwm modulation, it is a very important kind of modulation of a digital signal, for which the average, in which you choose the average. So you have a square wave with fixed frequency and average that depends on the high value, the time which this waveform stays high. And you see that with a timer you can do it by setting a comparison value during the counting. When you reach this comparison value, you flip the GPIO, and then when you reach the arrival value, you will go down. Now let's go to your serial communication. You need to be able to interface with a lot of different integrated circuits, which can be specific sensors that give you already a digital signal. You can communicate with other microcontrollers, with your Bluetooth and so on. And for that you have several protocols that maybe some are easier to implement, some are harder to implement in certain scenarios, some require less GPIOs, some more. And you have proprietary also protocols that you will need to do by yourself. Okay, let's speak about the Uart, Universal Asynchronous Receiver Transmitter. It is the implementation, like in the bus, it is pretty easy. You have just two signals, plus of course the power supply and the ground, that will carry the data transmitted from device 1 to device 2, and the other the data from device 2 to device 1. It is asynchronous, meaning the communication can start at any time, and there is a synchronization that needs to be done, which is done by the start bit. Then it means that it consumes a bit more energy because of this synchronization, but it is you have unfortunately the possibility to only connect two devices, which is a very big restriction in some cases, of course, but the communication is full duplex and it is very easy to implement. The serial peripheral interface is a protocol that is quite a bit different from the Uart. You see that it's first of all a synchronous type of communication, meaning that you need to have at least one signal for the synchronization. You see that you also have here the possibility to have a full duplex communication like a Uart, meaning that both devices that are communicating can both receive and transmit at the same time. Furthermore, you have that in this case you can communicate one master device, there can only be one unfortunately, with more slave devices. The only condition is that to communicate with one device you need to select it with a chip select. In total we see that we have four wires required for SPI communication, plus of course the ground again and the power supply again. You can implement SPI with 3 wires communications instead, fusing the MOSI wire, master output, slave input, with the MISO wire, master input, slave output. And of course, in that case, you need to organize the communication in such a way that both devices are not trying to contend the single wire, making a mess. So, it is widely adopted and it can be lower power than an E2C communication. It is also very flexible as long as you can make the hardware wiring for each slave device. But then again, the drawback is that if you want to add a new slave device, you need to make the hard wiring, and then there is no start error check, unfortunately, meaning that your manufacturer can add it, or you need to do error checking by yourself after you receive the data. Then you have more wires than an E2C communication. Let's now speak about inter-integrated circuit protocol, E2C. You see that it is a synchronous type of communication like SPI, but in this case it only needs 2 wires, which can be pretty cool. You have one wire which is for a serial clock, one wire which is for the serial data. Then of course to this you need to add the ground and the supply, of course. Every device is connected to the same serial clock, and every device is connected to a serial data. Everyone is connected to it via open drain. So you need a pull-up resistor for the serial clock and for the serial data. Effectively, this makes a small network like when you connect your computer through Ethernet. This is both a good thing because you only need 2 wires, and when you add a new device, you just assign it an address and you can communicate with it fast without making hardware changes. And unfortunately, the bad thing is that it is a bit more complex to manage, because you need to be able to identify each, of course, device by its, first of all, address. And then there is the possibility, since there is no master and everyone is at the same level, it is possible that all devices will try to communicate at the same time. Meaning that you can have a bus contention that can kill your communication and leave the bus hanging without any response, which is bad. You need a way, of course, meaning to reset the communication in case of bus contention. You have also an overhead to the transmission, because of course when you want device 1 to communicate with another one, you need to send the address before the communication starts.